this lecture we will cover some basic chemistry concepts. So to first understand how chemistry will apply to us within the clinical laboratory field, we must kind of see how chemistry kind of branches out within a wide variety of topics. So the knowledge of chemistry is very central to understanding some very different scientific disciplines. And so this chart here kind of demonstrates some of the different working relationships between different fields of science. And so as you can see, the medical field kind of branches off of this, which will kind of include some of the chemical, biological, molecular concepts, including toxicology, immunology, hematology. All the various subjects within the laboratory are going to kind of be encompassed within the field of chemistry. So we're going to kind of talk about some of the basic concepts that will kind of narrow us down to the laboratory science clinical aspect of chemistry. Chemistry is the study of the composition, properties, and interactions of matter. Over the years, there's been many attempts that have been made to understand the behavior of matter, and this can extend as far back as more than 2,500 years ago. Now, chemists study and describe the behavior of matter and energy in 3 different domains. That will include a macroscopic domain, and this is what we're most familiar with because in this realm, everyday things are large enough that we can sense them, we can touch them, we can use our senses and sight to observe the different properties of this matter. With the microscopic domain of chemistry, you kind of have to think about it in terms of being something really small that we can't see with our eyes. When we talk about micro, we talk about small versus macro, which is larger. So macro we see with our eyes, whereas micro we typically can't. They're very, very small. And so to look at these different components, we have to observe through a microscope or something that looks at the different properties that make up or the composition. We have to look at it at a more molecular, smaller level. This symbolic domain contains a specialized language that is used to represent the various components on the macroscopic and microscopic level, and this is going to be represented by something like a chemical symbol. Now, to kind of give you an idea of the difference between the 3 of these, we use this example here to the right where we are looking at the different levels. So if we look at the microscopic level, this is going to be more of like the gas molecules, the things that we can't really see. And so at this level, the organization of the molecules within it are not very close together. They're kind of spread out. And then as it comes to a more solid state, it's a little bit more of a structure to it. Versus once you get to a state of being more liquid, you can see that there's a variation between the structure and how it's made up, the links and the bonds. So we're going to go a little bit more detail of some of the different properties of matter, and we're going to discuss that a little bit further. So first we must understand, what is matter? Well, matter is anything that occupies space and has mass. Mass is a measure of the amount of matter in an object, whereas rate refers to the gravitational pull that it is exerted on that particular object. Now, the 3 most common states or phases of matter are going to include a solid, a liquid, and a gas. Now, a solid is very rigid. It possesses a definite shape, so we think of something that's more contained. It has an actual something that you can hold. You can see it, you can hold it, you can hold it in your hand if you need to, and you can observe the various properties of it. A liquid is something that flows. It takes the shape of the container that it is in, whereas a gas, it takes up both the shape and the volume of the container, so it's going to expand out and it's going to fill the whole container that it's in. So a solid, again, if we kind of refer to our last image, a solid would be like the ice cube versus the liquid, the water, and the gas would be kind of what is in the air and the atmosphere. Now, there has been a 4th state of matter that has been added over the years, and this will be plasma. So plasma is a gaseous state of matter that contains an appreciable amount of electrical charged particles. And so plasma has very unique properties, and these are distinct from ordinary gases. And it can be found in high temperature type environments. So naturally this would be something that's in stars and lightning. And then when we look at something that's man-made, an example would be some of your plasma television screens, or even a plasma torch that's used to cut metal, and there's an example of that here. When we talk about matter, we got to keep in mind the law of conservation of matter. This means that there is no detectable change in the total quantity of matter that's present when the matter converts from one type to another type. So if there's some kind of change that takes place, it doesn't matter if it's chemical or physical, then there's no detectable changes in the quantity of what is present. So the mass of beer precursor molecules are the same as the mass of beer product. So the sugar has become alcohol and carbonation, so it's kind of been broken down. The mass doesn't change for what is in there, or the properties itself don't really change. They just kind of go from one thing to another. So you've got that sugar that's converting down to the alcohol. The sugar's still there, it's just been converted to a new form. So that's kind of an example of understanding that what's actually present in there is not there. It's just done some rearranging to make something that's a little different than what it originally started as. Elements are a type of pure substance that cannot be broken down into anything that's any simpler by any sort of chemical change. Now, there are about 118 known elements that are displayed on a periodic table, and of those, over 90 occur naturally within our environment. So this would be like within the ocean, the Earth's crust, in the atmosphere, and 24 or so of those have been created within a laboratory. So a pure substance has a constant composition. It consists of only one element. And so an example of this would be something like gold, phosphorus, oxygen. We have some examples here, so you can see where those elements are combined together to just make up that molecule. And then within our compounds are also pure substances, but they can be broken down into simpler substances or elements by chemical changes. So they consist of 2 or more bonds of elements, and those are chemically bonded. And so examples of this would be water, glucose, carbon dioxide, and you can see here where you have some examples of compounds and how they're kind of chemically bonded together to make up something different. A mixture is composed of 2 or more types of matter that can be present in a varying amount and can be separated by physical change. So evaporation is an example of a type of physical change. So with evaporation, we know that with the previous examples where the water can evaporate up into the air, or you have ice that melts down into water. So there was a physical change that takes place to cause that mixture to have some sort of change. Now there are 2 types of mixtures. We have a homogeneous mixture, which exhibits a uniform composition, and it appears visually to be the same throughout. So like water could be a homogeneous mixture. It appears to be the same throughout. And so another name for a homogeneous mixture would be a solution. And so we're going to talk about this more as we kind of explore chemistry. Now a heterogeneous mixture has a composition that varies from point to point, and it is not uniform. So some more examples, like a heterogeneous mixture would be like oil and water. So the 2 of those, the composition of that is not uniform, like with lava lamps or anything like that. The 2 substances usually don't combine. Even if you try to mix them up, they're going to separate back out. But something like a sports drink, it has a homogeneous mixture. You have the various electrolytes and minerals that are throughout that. You cannot see a difference in them if they separate. You do have some things that over time will separate. So if you've ever had like a bottle or a plastic bottle of like Coca-Cola or something that maybe you saved when they were putting the names on the bottles, and you saved that Coca-Cola bottle. When you first purchased it, that it was just regular Coca-Cola, but as it sits over time, those sugars and things start to separate back out. So we know that matter is anything that has mass and takes up space. So we all matter. But depending on the properties of any given substance, we can further classify what it actually is. So when we look at matter, we have to ask the question, does it have a constant property or composition? If it does not have a constant property or composition, then we know that it is a mixture. And then from there we can determine, is that mixture uniform throughout? If that mixture is not uniform, then we know that it is a heterogeneous mixture. However, if it is uniform, then we know that it is a homogeneous mixture. So again, this is that oil and water versus something like a sports drink. Now, if matter does have a constant property and composition, then we know that it is a pure substance. And from there, it can further be, we have to determine whether or not it can further be simplified. If it cannot be further simplified, then we know that it is an element. However, if it can be, we know that it is a compound. It is a combination of something. To understand the various elements of periodic table, then we have to break it down to a more molecular level. So to do that, we have to look at and determine what is an atom. Well, an atom is the smallest particle of an element that has the properties of that element, and it can actually enter into a chemical combination. So it is what is actually going to compose or come together to actually make that element. Now, this idea was first proposed by the Greek philosophers in the 5th century. But later on, around the 19th century, John Dalton of England supported this hypothesis with a quantitative measurement. And so he's actually able to kind of prove this theory. So a molecule consists of two or more atoms that are connected together by forces, and these are known as chemical bonds. So we have the actual atom, and then that combines together to make the whole molecule, which is part of an element. And so if we kind of look at it in a backwards reverse point of view, we think about a cotton ball. So a cotton ball, we can see here in image A, you know, what cotton looks like on a plant. And then from there, we can look at it from a microscopic point of view. And so if we kind of zoom in, we can start to see the fibers. For the image B here, you can see the fibers up under the microscope. Now, if you were to zoom in on those fibers and look at it with an electron microscope at a higher magnification, then you're going to start to see it, see those fibers as strands combined together. And then from there, if we were to kind of break it down even further and start getting to an atomic level, then you can start to see where those bonds are taking place, and you have the different bonds that are stretching out over those strands to make those fibers, and then you can break it on down to E when you actually start getting at the various elements that combine to actually make that cotton. The characteristics that help us to distinguish one substance from another is called properties, and that can be divided up into physical and chemical properties. Physical properties are the characteristics of matter that are not associated with a change in the actual chemical composition. So this will be things like the density, the color, the hardness, the melting and boiling points, electrical conductivity. So a physical change is a change in the state of the properties of that matter without any sort of chemical composition change. So if we think about something like butter, if you put butter on a stove, melt it in a pot, it's going to melt into a liquid state. However, if you remove it from the heat, it starts coming back to room temperature, then it's going to solidify and take the shape of that particular pot. Water is another example. So the steam will kind of start to come up. It'll condensate around the lid, and then it'll drop back down and return back into the water. So you have that steam change based on the heat and the evaporation and whatnot. Now, when we talk about a chemical change, the change of one type of matter into another type, or the inability of something to change is its actual chemical property. It's a change in the composition. And so examples of this would be the flammability, toxicity, acidity, the reactivity, heat of combustion. And so here we have an example of iron versus chromium, whereas you know that iron will rust, whereas chromium will not. So that's an actual chemical property or change in the composition of that particular matter. Atoms and subatomic particles are very small, with the diameter of an atom being approximately 10 to the negative 10th meter, and the diameter of the nucleus itself being about 100,000 times smaller at approximately 10 to the negative 15th meter. So to kind of put that in proportion for you, if you were to take a blueberry and just place it in the center of a football stadium, that would be the size of the nucleus compared to the actual entire atom itself. So the stadium would be the actual electron cloud, whereas the blueberry would be the nucleus. Now the nucleus contains the majority of the atom's mass, which is kind of a hard concept to grasp considering that it's so small. So when we look at trying to figure out the actual mass of the atom and knowing that the nucleus contains a bulk of it, we have to actually look at it in smaller units in order to do those measurements. And so those units that we use are actually going to be the atomic mass unit. And so the atomic mass unit, one atomic mass unit equals approximately 1.6605 times 10 to the negative 24 grams. And we're actually familiar with the measurement of grams, so it kind of makes it a little bit of an easier concept for us to grasp. Now when we look at the charge of it, charge is actually measured out in coulombs. So that C there doesn't actually mean charge. It is the actual electrical unit of measurement that is used for this. And so the actual charge for these is represented as 1.602 times 10 to the negative 19 coulombs. And so we can actually translate the mass of it, and we can kind of use the charge of it to kind of figure out the different different properties of each particular atom. And so when we talk about the neutron and the protons, which of course are located within the nucleus, we can understand that the nucleus itself is going to have a positive charge because of that proton. The overall unit charge for a neutron is neutral, so it's represented as 0, whereas the charge for the proton is a positive charge. And so if we also look at the atomic mass unit and we look at it in terms of grams, then we know that a bulk of that mass is actually going to be in that nucleus just simply because of how we can kind of measure out that atomic mass unit. The electrons itself are going to be outside here, outside the nucleus in an orbital, where they're kind of going around in circular orbits around this nucleus. And so this whole outside part here is going to be like the electron cloud. And so basically this kind of breaks it down into the actual structure and the symbolism of the various atoms. So now let's talk a little bit more about the periodic table and what the different things of the periodic table and the symbols mean. So a chemical symbol is a symbol that is abbreviation that we use to indicate a particular element or an atom of an element. And so an example of this might be something like mercury. So if we look here on this periodic table, we can see that mercury is kind of located here in this area. And then this particular periodic table kind of gives you a little bit more of information based off of the color of that box, tells you that it's a metal, and the fact that it's written in blue tells you it is a liquid type metal. So we do know that mercury does take more of a liquid form if you think about the older thermometers in which the mercury was in there. So some symbols are derived from common names of the elements, whereas some abbreviations are based off other language. So mercury obviously would be an example of that. Now if we kind of look at each of them individually, and then we kind of learn about what all of this information here means. So for example, here with hydrogen, we've got the symbol that actually indicates what the element is. So you have that represented as an H. And this can sometimes be 1 or 2 letters, but occasionally you do have some that are 3 letters. And this describes elements that have atomic numbers that are greater than 12. So you can see some examples of those here. And then from there we have the symbol. We also have the atomic number. That's for this particular chart. It's up here in the corner. And we also have the element's name, as well as we have the atomic mass. Now you can see the layout of this can be sometimes a little different depending on the actual chart. Some stuff may be included, some stuff may be removed from it. So it just depends on the chart that you're actually looking at. Depending on the particular periodic table, you can see that the symbol itself can be represented a couple of different ways. But again, this particular image here, we see that X represents the actual element symbol, or represents the abbreviation to the name of that element, where we have A equals the mass number. The mass number itself is representative of the protons plus the neutrons. And we also have the atomic number, and the atomic number is represented by Z. And that's going to equal the number of protons that's actually in that particular element. So a neutral atom must contain the same number of positive and negative charges, and the number of protons is actually going to equal the number of electrons. So therefore the atomic number also indicates the number of electrons that are in a neutral atom. Now it has to be neutral in order for that particular scenario to exist. There are cases where you can have different charges there, but we're just talking about a simple structure at this point. You can see these written out in different ways. This particular example here from the online textbook is going to show the mass number in a different spot. Some charts may omit the actual atomic number, and some may actually include the charge itself. So you got to kind of be familiar with what you're looking at, the particular chart you're looking at, so that you know where everything is represented. Here in this particular example, you have the atomic number above the actual element symbol, and then you have the atomic mass listed below. And notice that the atomic mass is listed in the AMU. Neutrons are actually uncharged, and if you want to find out how many neutrons are in a particular element, you would subtract that atomic number from that mass number. So a neutral atom does contain the same number of positive and negative charges, and the number of protons equals the number of neutrons. Therefore, the atomic number also indicates the number of electrons that are in a neutral atom. Now, isotopes are atoms of the same element that differ in mass, but they have the same atomic number. So they have equal number of protons, but there's some variations in the number of neutrons and electrons, the neutrons that are in the nucleus. And so the symbols for these specific isotopes of any element is actually written by placing the mass number as a superscript, but you put it to the left of the element instead of to the right of the element. And the atomic number is sometimes written as a subscript. So you can see this kind of written a couple of different ways. But all isotopes have 12 protons, but the number of neutrons can be different. Now when something is not neutral, it's an ion. So when the number of protons and electrons are not equal, that particular atom is going to have a different charge to it. It's going to be electrically charged, and this is considered an ion. The charge of an atom is actually the number of particles minus the number of electrons. So within an atom or a molecule, they acquire this charge by losing or gaining electrons. So any atom that loses one or more electrons will demonstrate a positive charge. This is called a cation. Whereas any atom that gains more electrons will exhibit a negative charge, and this is an anion. So now when we're looking at ions and anions and looking at the different charges and things, how that helps us in the clinical lab is to understand the concept of mass spectrophotometry. And within mass spectrophotometry, the occurrence of and natural abundances of isotopes can be experimentally determined using an instrument called a mass spectrophotometer. And so what you do is you actually take the sample, you enter it into the analyzer. The sample is actually vaporized, it's exposed to a high energy of an electron beam, and it causes the sample's atoms or molecules to become charged. And in that charge, they're going to become more active. So typically this happens because they're either losing one or more of electrons. And so the cations can then be separated based on their mass and their charge, and then that's how you kind of figure out what is actually in that sample when you're looking for those particular ions or isotopes.